Hello everyone, welcome to this session on building a multi-tenant vector database using Amazon Aurora Postgres. My name is Nihilson and I am a solutions architect at AWS. Today, in this session, first we are going to talk about some of the basic concepts of vectors. Next, we'll explore Amazon Aurora Postgres and its vector database capabilities. Then, we'll look at how we can implement vector databases and with an example architecture. Then we discuss how to enable multi-tenancy and tenant isolation in vector databases. Finally, we'll wrap it up with a demo. Let's get started with some basic concepts around vector databases. What is a vector? In the mathematics or physics world, a vector is actually a quantity that has both magnitude and direction. And usually you represent it by an arrow and whose direction is same as the quantity and their length is proportional to the quantity's magnitude. Let us just keep aside this mathematical and physics definition and get into the context of AI ML. In the AI and programming world, you can think of vectors as an array of numbers that represents a sequence of byte or text. And we have several foundation models that helps you convert input data to vectors. And it is this input data which can be in the form of a text, images, audios, and videos. And here you see an example of a text that is converted into a vector representation. That is an array. And arrays have fixed length. And it is this length is represented as the dimension of the vector. And each foundation model has a fixed dimension for the vector that it deals with. Typically, the higher the dimension, the better is the model's performance. The term vectors and embeddings are often interchangeably used. They both represent the same numerical representation, but there is a subtle difference. The term vector just refers to the array of numbers with a specific dimensionality, whereas embeddings refers specifically to the technique of representing data as vectors in such a way that it captures some meaningful information, semantic relationships, or even the contextual characteristics. Now, this actually opens up a concept of LLMs, the large language models that are actually embedding models. And vector data stores make use of these embedding models to encode or convert raw data into vector embeddings. Now, if you take Bedrock as a service, it provides several foundation models, and particularly from an embedding model perspective, you have these Amazon Titan embedding model and Cohere embedding model. Let's understand what is a vector database and how a vector data store environment would look like. So data is the core of any AI and generative AI application. And data exists in multiple formats: structured data or semi-structured data or unstructured data. We have been using relational databases to deal with this structured data and also to some extent the semi-structured data. With relational databases, you have to kind of use the traditional keyword-based searches or metadata-based searches. However, storing unstructured data formats like documents, images, audio, video, etc. is not ideal with relational databases. Now, with the advancement of AI and particularly the generative AI enabled application, there's a need to do similarity search or semantic search. Hence, instead of storing the raw data as is, we convert them into something called dense vector embeddings and store them in a vector database. We make use of embedding models to encode or convert the raw data into vector embeddings before storing into the vector data store. Here, we use Amazon Bedrock service that provides several leading foundational models and LLMs. And we use Aurora Postgres as the underlying vector data store. Now, we just learned about these LLMs, right? Large language models. So large language models are kind of trained with massive data, usually public data, library data. They do have some challenges because they are trained with static data and the general data. And that's because their responses are not accurate, or maybe they are not related to your own domain or data. Now, this can result in hallucination, and where they can generate text and can confidently state a false fact. How do we overcome this? There are several mitigation approaches. One, the prompt engineering. Two, you can use you can fine tune the model with domain specific data. But the more commonly used approach is something called retrieval augmented generation, RAG. So RAG is a solution to overcome the challenges with LLMs. Now, if you look at this diagram there, RAG has two phases. The data ingestion workflow phase, what you see at the bottom, and the text generation workflow at the top. And in particular, there are like about 5 key stages in a RAG process. One, it starts with your data. So you ingest your data into a knowledge base so that it gets stored into the vector database. Then once the ingestion is complete, then a user typically submits a query. That's the step 2 there. When the query is then converted into embeddings or vectors using an embedding model, and then the vector embeddings are kind of used to make a semantic search. That's the step 3 against the vector data store. So once we get some response back from the vector database, we call this response as the context. That's the context information that's useful. So you kind of use this response to augment it into your prompt that's going to be sent against the large language model. So the prompt essentially is now a combination of your original natural language query as well as the context that you generated or you retrieved from the vector database. Now this augmented prompt is more contextual. It has more context about your business, about your domain. And with that, the LLMs can generate more appropriate response back to you. Now let's look at some of our AWS services that provide the vector capabilities. So we have this service, Amazon OpenSearch. OpenSearch provides vector capabilities through its KNN plugin. Then we have Amazon MemoryDB. It recently, back in July, they added support for vector database. Then we have our Neptune graph database and Amazon DocumentDB also supporting vector capabilities. Further, we have both Amazon Aurora and RDS Postgres, both supporting vector database. Today, we'll focus on Amazon Aurora Postgres for our vector database. Let's explore Aurora Postgres as a vector database provider. How does Aurora provide vector capabilities? Aurora and RDS uses what we call PG vector. It is an extension to provide vector capabilities. Now, what is this PG vector? Postgres has a mechanism called extensions. So you typically use this extension to plug in new features. So PG vector is one such Postgres extension feature that adds vector database and similarity search capabilities. Now, PG vector supports storing vector database vector embeddings that allows us to use for RAG approach. Both Aurora Postgres and RDS Postgres supports this PG vector extension. Once you install this PG vector extension, you get a bunch of features. We'll explore them in the next slide. PG vector adds support for storage of vector embeddings through this new data type called vector. So when you create a table, you would designate a column for your vector embeddings and use a vector data type for it. Next, PG vector adds support for indexing for improving performance. It supports 2 types of indexes, HNSW index and IVF flat index. HNSW index has better query performance but slower build times and it uses more memory. IVF flat index, on the other hand, has faster build times and uses less memory but lower query performance. Now, PG vector also supports both exact nearest neighbor and approximate nearest neighbor search algorithms. Now, how do you choose between them? It is usually the recall versus performance trade-off when you have to choose between these search options. pgvector supports co-locating your vector embeddings along with your metadata, or you can use your transactional data as well within your vector table. Then you also have a choice of different vector distance operators like the Euclidean distance, cosine distance, negative inner impact, inner product, and taxicab distance. Amazon Aurora has several features that complement vector workloads. One of the important features is this optimized reads with this tiered caching capability. The tiered caching capability automatically caches database pages that gets evicted from in-memory database buffer pools. This helps vector workloads to be more performant for applications, especially with large data sets that exceed the memory capacity of a database instance. The next feature is the graviton support. So you get better price performance with Amazon Aurora when you use graviton instances for your vector workloads. LangChain, integrating your GenAI applications with pgvector using open source frameworks like LangChain simplifies your semantic search over your vector data. Now, another aspect is the native integration of Amazon Bedrock with Aurora. So you kind of have two options to enable this integration. You can use the Amazon Bedrock knowledge base feature, or you can use the AWS ML extension for SQL-based integration. And now we have a graph here from a benchmark that involved a vector database workload. And in this case, it was measured using Aurora Postgres with the IO optimized tiered caching enabled. And as we can observe that with pgvector workload, this combination actually scales or increases your queries per second up to 9 times, especially when your workload exceeds available instance memory. Let's move into understanding the different vector database implementation. There are a couple of ways you can think of implementing vector database environments for your generative AI application. One, the self-managed approach, where you own and write all the required SQL queries against your PG vector, especially for your data ingestion and retrieval requirements. The other approach is the AWS managed, where we use features like knowledge bases for Amazon Bedrock and use its API. So this kind of abstracts all the manual writing queries or building data integration flows for you. And here is an example architecture of how you can implement a vector database environment using a AWS managed approach. You have 3 main components here. One, your Aurora Postgres vector database at the right top. And then you have this Amazon Bedrock knowledge base. Then you have the data source, which is the Amazon S3 bucket. Now, in this architecture, I would consider there are like 4 different processes involved to build this architecture. First, you need to provision your vector database, right? Along with that, you also have to create knowledge bases, and you also have to configure your data sources like the S3 bucket. The next is the ingest phase. So in ingest, you typically upload your documents into your data source, in this case, the S3 bucket. And this kind of kickstarts the ingestion process through an API call. Knowledge base actually abstracts this document chunking strategy, especially when you deal with large documents. These documents typically get broken down into smaller chunks for efficiency and performance reasons. The next step is, after you ingest your data and it is available in your vector store, you kind of go and run a natural language query to retrieve similar vector data or similar data chunks from your vector database. Then once you get the data back from your vector database, you kind of move into this augment phase, where you combine your original query along with your retrieved vector data. And then you construct a prompt before sending it to the actual LLM to generate a response or answer for the user. That's the kind of architecture we are going to look at. We'll look at all these stages in detail in the next slides. First, you kind of provision the vector table. So what you see on the right is a code snippet of the SQL script that you might need to provision your vector database tables. So you start by creating an extension to enable PG Vector plugin. Then you create a schema and a table. Then the third step is you create an index, and in this case, as you can see, we are using this HNSW index type. Then finally, you create some users, Bedrock user as you see here, and then grant permissions for these user. Now, once this schema and the tables are provisioned, then you are good to go with the next phase of the vector database environment. Now, the next step is ingesting vector data. But before you can ingest vector data, we need to create Amazon Bedrock knowledge base. Now, what is this Amazon Bedrock knowledge base? Knowledge base is a fully managed capability to implement RAG process, specifying or simplifying the ingestion, retrieval, and augmentation. So once you create the knowledge base, you can then configure a data source. You can use S3 as your data source to input your documents. Now, recently, knowledge base added support for other data source types like Confluence, SharePoint, Salesforce, and even a crawler to crawl web pages. Once you have data input to your data source, then you can just kickstart the ingestion by invoking this start ingestion job API. This will actually store your data into the vector database. Now that we have data in our vector database, we can move on to this retrieve phase. So here, as you can see, you just have some natural language query. The example in the top, you can see what the question is, what is the condition of the roof, right? And then we are going to make use of the knowledge base API called retrieve. And we simply pass this query as one of the parameter along with other configurations like how many number of vector data chunks you want to retrieve. And as you can see at the bottom, you have a sample output showing 2 chunks of data that has been retrieved. Of course, the data has been trimmed for simplicity. Now, there are a few other attributes in the retrieved content. As you can see, it also has metadata, like it gives the location of the original data or the document from where this data chunk came through. Then it also adds you a score to indicate the efficiency of the underlying search was used. Right now, once you have some data retrieved from your vector database, essentially in the form of chunks, you move to the next stage called augment, where you augment your prompt with this retrieved vector data. So what you see here is an example prompt structure where you have this section called context. Within the context, you embed your retrieved vector data chunks. And then along with that, you also add your original user question, the natural language question. So now this prompt becomes more contextual to your own data that you got from your vector database. And what you see at the bottom is a sample output from one of the large language model, which generated the response based on your question and also importantly based on the vector chunks that you passed in your prompt. And it is a human readable form to the question, what is the condition of the roof? And it has nicely described the condition of the roof. Now, let's move into the topic of multi-tenancy. With vector database, particularly when we are using Amazon Aurora Postgres, you kind of have 2 options. One, the native Postgres row level security, especially when you do the self-managed, when you build a self-managed vector database. On the other hand, we can explore how knowledge base supports multi-tenancy for Amazon Bedrock. Now with Bedrock Knowledge Base, there is a feature called metadata filtering. So we are going to tap this feature and explore how we can achieve tenant isolation. So what you see on the top of the screen on the right is some sample documents. So we have documents like home survey documents for 5 tenants, okay, tenant 1, 2, 3, 4, and 5. Now all that you need to do is add a metadata JSON document for each of these documents, and then within the metadata JSON, you need to add the tenant identifier information. So the highlighted section at the top right is what it would look like in a metadata JSON file. Now, once you have this, you kind of ingest these metadata JSON files along with your document. Then you make use of a modified retrieve function where you pass in the tenant filter, where you can pass the tenant ID as a filter. Of course, you can have complex filter conditions as well. Now, this is going to be a very useful mechanism to achieve tenant isolation, especially when you use Bedrock Knowledge Base for your vector database implementation. Now let's move to the demo section. Now that we have learned about AWS managed approach of implementing vector databases, we can check all that in action through this demo. We're going to make use of Amazon Bedrock Knowledge Base for the managed RAG and Aurora Postgres Serverless V2 as our vector database. What you see here is our Jupyter notebook. This has all the necessary steps to provision, ingest, retrieve, augment data from the vector database. We are also going to look at how to implement tenant isolation. We do have some prerequisites listed here, like mainly the Aurora Postgres cluster with RDS data API enabled. I've already pre-provisioned Aurora Serverless V2 environment with RDS data API enabled. Now, the next step is to begin the provision part. So here is our schema or the SQL related to creating our vector database. What I'm going to do is copy this and kind of use this query editor feature of RDS, and I'm going to run those commands and let's explore the output. What you see here, let's check the status. Now all the commands ran successfully. Let's now shift to the Jupyter notebook. Here we have some configuration steps which I have already run. Now let's start with this function to upload documents to S3. So let's look at some of the data sets or documents we're going to make use of for this demo. Here you see 5 documents, home survey documents, tenant 1, 2, 3, 4, and 5. We're going to make use of this for testing the purpose. And let's look at one tenant 1's document. What you see here is a home survey document. It has both images and textual information. And we're going to make use of this for our testing purpose of the vector database. Now switching back to the Jupyter notebook, let's start with the steps that we need to follow. First, let's create a Bedrock knowledge base, and the configuration that you see here corresponds to our vector database that we just provisioned. Let me run this and let's just, okay. Yeah, the knowledge base has been created. Now the next step is for us to create a data source. Let's use an S3 bucket. I'm going to run this cell, and this creates our data source configuration in the knowledge base. Now I'm going to add some documents into the data source. I'll add the tenant 1's document by running this cell to invoke the upload file to S3 function. So this will upload the tenant 1's document to the S3 bucket. Once that is done, let's move on to the ingest step. So here I'm going to just invoke the start ingestion job API of Bedrock knowledge base. So I'm going to run this cell, and this will kickstart the ingestion process. Depending on the document number or document size, the ingestion can take time. It will take a few seconds. So until the ingestion happens, let's review the next step, which is retrieving the vector data chunks. Here, as you can see, we are going to make use of a natural language question, like what is the condition of the roof, right? And then we're going to make use of the retrieve API of Bedrock knowledge base. So once the ingestion into the vector database is complete, yes, now we can invoke this retrieve step. So I'm going to run this, and let's explore what data it retrieves for us. Nice. So it has retrieved couple of chunks, okay, couple of vector data chunks from the vector database. Now what you're going to do is augment these vector data chunks into the prompt. So here we are combining the original natural language question along with the retrieved data chunks in the context section of the prompt. And once the prompt is augmented with the context information, we're going to send it to an LLM to generate a response. So that's so here is how the augmented prompt looks like, and we're going to invoke the next cell, which is step 7. This will actually invoke an LLM. We are using Claude as a LLM, and let's explore what response it has generated for us. So a nice response to the question, what is the condition of the roof? So this is quite readable, human readable, and with the context data that we provided from the vector database. Once that's complete, we just dealt only a single tenant. Now let's add more tenants. Okay, let's add additional tenants. I'm going to add tenant 2, 3, 4 and 5's data. I'm going to upload them into the S3 bucket, and then step 9, I'm going to kickstart the ingestion process so that these new uploaded documents gets ingested into the knowledge base and to the vector database. Now let's wait till this is completed, till the ingestion is completed. The step 10 is, when the ingestion gets completed, we're going to retrieve the vector data related to tenant 3. So I'm going to run a question like, what is the condition of the roof in my survey report, but for the tenant 3. Let's run this cell and I explore what response we get after the ingestion is over. Okay, let's just wait for the ingestion. It will take a few more seconds. Okay, the ingestion is over. Now I think we can run this step 10. Yes, and it has retrieved some response. Let's explore the response that it has retrieved. So interestingly, it has retrieved like about 5 chunks, but unexpectedly, you see, we wanted data from tenant 3, but it has got tenant 1, 5, 2, 1 and 4, right? This is not what we want in a multi-tenant environment. Now let's think about how we can address this. Like we know that knowledge base provides a feature called metadata filtering. We're going to use that to tag each tenant document using a metadata information. So here is how the metadata information would look like. We have this tenant ID attribute mapping. We are going to tag this for all our documents. I've already tagged them. Now let's run this cell to upload all of these metadata JSON for all the tenants documents. Okay, once the upload is complete, then we can kickstart the ingest process so that these metadata JSON also get stored in the vector database. Now, once these metadata along with your original document resides in the vector database, then it helps us to run retrieve operations with tenant filtering enabled, right? Now, here is the modified retrieve function with filter. So we pass the tenant 3, and let's explore what results, what data chunks this operation brings us back. Okay, I'm going to run this cell. Oh, nice. So it has bought a couple of data chunks, and like we intended, it just brought data chunks from tenant 3. So both the data chunks were from the tenant 3 as we expected. So this is a powerful mechanism to implement tenant isolation for vector database, especially when you are using Bedrock knowledge base as a managed mechanism. Here are some of the resources that you can make use of. These are the links to the Jupyter notebooks that we saw in the demo. Thank you, everyone.